Hi everyone. So today in this video, I will be explaining you the problem Xoring the Subarrays from interviewbit. So let us first read the problem. The problem says that given an integer array A of size n, we need to find the value obtained by Xoring the contiguous subarrays followed by Xoring the values thus obtained. So we need to determine its value and return it. Let me explain you what the problem says. The problem says that we are given an array. Let's say the array is given like this. Let's say it is a0, then a1, then a2, so on and so up to, let's say there are n elements. It becomes a of n minus 1. So what we need to do is to take every contiguous subarray, right? Take every contiguous subarrays and find its XOR, and then XOR all the XORed values over all the subarrays, right? For example, let's say if the array is like something like this, if it is 2, 3, or let's say it is 5, then 7, then 8. Let's consider only these three elements. Then what we need to do is to find the XOR of all the contiguous subarrays. So let us see what are all the subarrays we have. So the first subarray can be consisting of only one element, 4, or we can have only 7, or we can also have only 8, or we can have like 4 and 7. Actually these are all contiguous subarrays of size 1. Now we are noting down all the contiguous subarrays of size 2. For example, here it is 4, 7, and then 7, 8. So then we have 7 and 8. And then if we note down all the subarrays of size 3, then it is 4, 7, and 8. Okay, and so if you just determine the XOR values, so the XOR value of an array consisting of only one element is the element itself. So it is 4, then it is 7, and then it is 8, then it is 4 XOR 7. It will be 4 XORed with 7, which will be 100, XORed with 111, which actually comes out to be 3, right? So this is 3. Now let's consider this one. 7 XORed with 8, so 7 is 111, XORed with 1000, so that comes out to be 15. Okay, and similarly if you see this, then this is 100. I'm just writing down its binary representation and doing the XOR. So XORed with 100. Now this comes out to be 1, then uh, then 0, and then 1, right? Yes, so it comes out to be this, and this is nothing but this is 8 plus 3, which is 11. This is 11. Okay, so these were all the binary representations, and this is the decimal representation, final value, right? So now once we found the XOR of all the subarrays, as you can see, these XORed values are 4, 7, 8, 3, 15, and then 11. So what we need to return is the XOR of all these found values. So we need to return for XORed with 7, 7, and then XORed with 8, XORed with 3, XORed with 15, and then XORed with 11. So what we need to do, we need to just return this thing. Okay, and let's let's calculate this quickly. So if you just try to find the XOR of all these things, right? So it will actually be 4 is like 10, then 7 is like 111, then 8 is like 1000, and then 3 will be 11. Okay, then 15 will be 1111, and then 11 will be 1011. Okay, so if you just take the XOR of all, then this is 1111, it will be 0. There are 1 2 3 4 4 ones, again 0, 1 2 3, odd number of ones 1, then 1111. Okay, so the value of this comes out to be 12. So what we need to return is basically 12. Okay, so okay, so Okay, so what we need to return is basically 12. Fine. So how can we do this? Okay, so one way of dealing with this problem is to just find the XOR of all the subarrays, right? And then just take the XOR of all those resulting XOR of the corresponding subarrays. So what I want to say is that find the XOR of all the subarrays, all the subarrays, and take their XOR. Okay, take their XOR. So now, finding the XOR of all the subarrays. Okay, so now we know that there can be order of n square subarrays, right? Actually, if you are given n elements, then there exists actually n into n plus 1 by 2 subarrays. Okay, so obviously for n elements, so if we care about for n elements, there are these many subarrays. Okay, and there are these many subarrays. So if you just try to find the XOR of all these subarrays, then obviously it will be order of n square. Okay, if you just try to find, and one thing more, that these many subarrays are there, and finding the XOR of one subarray will again cost you order of n time complexity. Okay, it will need it can be done in order of 10 time complexity, finding the XOR of one subarray, XOR of one subarray. So obviously if you just find the XOR over all the subarrays, it will actually require order of n into the number of subarrays, and the number of subarrays are of the order of n square. So again n square. So that means that doing it naively will cost us will require a time complexity of order of n cube. Right? So this is the first thing which we can do, but can we optimize it further? Okay. So now you may think of that. Okay, finding the XOR of one subarray. Let's say the subarray is from L to R, where L and R are the indexes of the start and end of a subarray. So what you are doing is for finding the XOR of this subarray, you are just iterating over this interval L to R and just finding its XOR, and that's why it required order of n time complexity. But can we optimize it? Can we just reduce its time complexity? The answer is yes. Like we can use something called prefix XOR. Okay, you can use something called as prefix XOR. And what is a prefix XOR is something like this. Let's say you are having an array like a1, a2, a3, and let's say a4. Let's consider only these four elements. So their prefix XOR will be an array. So their prefix XOR will be an array which would be having its element as a1, a1 XORed with a2, then a1 XORed with a2 XORed with a3, and then a1 XORed with a2 XORed with a3 XORed with a4. What does it mean? Is that it will be having the XOR of the first I elements from the beginning. Okay. Now, so if you have this prefix XOR array, then in order to calculate the XOR of subarray from L to R, all you need to do is to do something like this. It will be nothing but prefix XOR of R minus prefix XOR of L minus 1. Okay, it will be it will be just this, and you can just see like why it is so. It's mainly because of this property of the XOR. XOR says that A XOR A is equal to 0. Okay, so whenever there are two same elements which are XORed together, you will be having 0. So if you take the prefix XOR of R, then it will basically be having A1 XORed with A2 XORed with A3 XORed with so on and so up to A of R. And if you are taking the XOR with a of L minus 1, it will be having a1 XOR with a2 XOR with a3 and so on and so up to a of L minus 1. So what you can see from here, that a1 is appearing here also and here also. So that's why they will XOR together to give 0. Okay, and 0 XOR with anything is the element itself. So similarly you can see that all these elements, okay, all these elements will just cancel all these elements from here up to a of L minus 1, and what we will be left with will simply be AL XORed with a of L plus 1, a of L plus 1 XORed with up to a of R, so which is what we required. So from here what we can see is that now for finding the finding finding the XOR of a subarray. Now what we can see that for finding the XOR of subarray, we are actually using an algorithm which is requiring O of one time complexity, right? We are just pre-processing the array by maintaining a prefix XOR, and then we are using that prefix XOR array to calculate the XOR of all the subarrays in order of one time complexity. Like for a particular subarray, we are just using O of one time complexity to evaluate the XOR. But still, even after doing this modification, we still need to evaluate the XOR of all the n square subarrays. So still our time complexity will be order of n square. Okay, but still from order of n cube we improved our solution to have an time complexity of order of n square. Okay, but can we think of optimizing it further? Like can we do it in order of n or order of n log n, or maybe order of n square root of n? Can we just have such a modification to have that thing? Okay. So for seeing that thing, what we do, uh, let's say we have an array. Let's have this array only. Okay, this array only, and we have already noted down all the subarrays here. Like we initially had the array as 4 7 and 8, and we wrote down the subarrays as 4 then 7 then 8 then 4 7 then 7 8 then 4 7 8, and we also calculated these values like 4 then 7 then 8 then 4 zord with 7. So what here we do is that let's don't evaluate it exactly. We just let us just only write their XOR in the expression form. So let's only write it as 7 XORed with 8. Okay, and similarly let us only write it like this: 4 XORed with 7 XORed with 8. Okay, and now if you just try to find the XOR of all these values, what you will get? You will get something like this, like 4 XORed with 7 XORed with 8 XORed with 4 XORed 7, then XORed with 7 XORed 8, then XORed with 4 XOR 7 XOR 8, 4 XOR 7 XOR 8. Okay, you get something like this. So this is what our answer will be. Okay, this will be what our answer will be. Now one thing you can see, that our answer is equal to the XOR of some elements. Okay, like it is 4 XORed with 7 XORed with 8 XORed 4 XORed 7. Okay, and all these elements like 4 7 and 8 are from our initial array, like 4 7 8. So you can see that there is no element which is not present in our input array. Okay, so one thing we can say, that our final answer, the final answer will be the XOR of some elements from our from our given array. Okay, but how do we find that which elements will be there in our final answer, or you can say in the final XOR value? So what we will do is that instead of finding the all the subarrays and finding their XOR and then XORing them together, what we do is we find we find the contribution of each element a of I and XOR them together. So what I mean by this is that let's say our array is like a1, a2 and a3. Okay, now what we do, we try to find that okay, in our final answer, or you can say in our final XOR, how many times will ai appear, how many times, we try to find how many times a particular value, or you can say the element at index I will occur. Okay, so now you may think of why this is useful. This is useful because if we know how many times a particular value will occur in the final XOR expression, then we can determine whether it will be present there or not. For example, if the AI occurs for even number of times in the final XOR expression, then we know that it will not contribute anything, because if there is an element, let's say x, and if we XOR it even number of times, then that basically turns out to be 0. And similarly, if it occurs odd number of times, then we will simply just take the element itself, because x XORed with x XORed with up to odd number of times will be x only. Okay, so that's why finding that how many times a particular element or the element at a particular index will occur can help us find the final XORed expression. So now we only try to see that how many times a particular AI will occur. Okay, so the thing is that if if you consider, let's say a1, a2, a3 and a4, let's say only 4 elements, and you want to see that what will be the contribution of this element, like how many times will this element appear in the final XORed expression. So actually it will occur only those many times as many subarrays are there which contains this element. For example, we try to find, or we try to count how many subarrays are there which contain this element. So let's say the first element, let's say uh, so this subarray will contain this is another subarray. Okay, then this is also subarray which will contain this, and this subarray will also contain this, and this entire subarray will also contain it. Okay, so as you can see, there are around 1 2 3 4 5. Okay, or are there many any more subarray? This is the first one, this the second. Yes, there are this there is like this subarray also. Yeah, so there are 1 2, then 1 2 3 4 5 6. Okay, as you can see, there are around 6 subarrays which contains this. Okay, so there are 6 subarrays which contain this. So that's why this a2 will occur 6 number of times in the final XORed expression. Now one thing you can see is that uh, yeah, did this all. Okay, so Let us try to see one thing, that if we want to say that okay, how many subarrays are there which contains this A2. Okay, so any subarray which contains A2 will be of this form. Okay, that subarray should be having the left index, or you can say the starting index, and that should be lesser than or equal to this, the index of the element itself, and the right bound, or you can say the ending point of the subarray should be greater than or equal to the index of the element, index of the this this given element, right? So for example, as you can see here, the index is 2, so obviously uh, so you can see that there are how many L values can be there. So obviously the value of L can the this L pointer can slide from 1 to 2. So there are like two values, and similarly the R value, or you can say the ending point, can slide anywhere from 2 to 4. So there are like 2, 3, 4. There are three values. That's why uh, the number of subarrays containing A2 will be 6. Okay. So in general, if you are given any array, so in general, if you are given any array like A1, then A2, then A3, so on and so up to, right? And you are given, let's say AI, let's say you are given AN, and okay, so if I assume that this is one based indexed, okay, then the number of subarrays, the number of subarrays containing AI will be equal to into I into n minus I plus 1. So this will be the thing. Okay, I, because you can see that here it was what, so for example here it was 2, then I know that there are two values of L, and there are around 4 minus 2 plus 1, which is 3. So there are three values of R. Okay, so there will be these many values. Okay, so once you know this, it's now quite simple. All what you need to do is to just uh, go for every element. So we just iterate over every element from left to right, or you can say from 1 to n. Okay, 1 to n, and we just calculate this number of subarrays. Okay, calculate number of subarrays, okay, using this given formula like I into n minus I plus 1, and then if it is even, then just keep that. Otherwise, if it is odd, then simply make your answer as answer XORed with that element, A of I, and then you just need to return it. Okay, so now as you can see, now this algorithm will run in order of n time complexity and order of 1 space complexity. Okay, and the algorithm which I described you in this first optimization, that was calculating the prefix XOR, it works in order of n by time complexity and order of n space complexity, because you are using O of n space to store the prefixes. Okay, prefix XORs space complexity. Okay, and this one will no, but this one final one, iterating from every element and then calculating the number of XORs, and from the parity of that number of XORs, number of subarrays, calculating the answer that runs in order of n time and order of space complexity. Okay, so you can we can actually optimize it even more further, just a bit optimization, and that is what, that if n is even, then the answer will always equal to 0. Okay? If n is even, then the number of then the answer will actually also always be 0. Let's see how. So let's think about this case. If n is even, okay, if n is even, okay, but before that, let us first run this algorithm on our sample only. So let us say we take this example 4, 7, and let's say we have this thing. Okay, so we first of all try to find uh, how many subarrays are there which will be containing 4. Okay, that will be what? That will be I into n minus I plus 1. So I is 1, 1 into n is 3, so 3 minus 1 plus 1, that comes out to be not 2, actually it comes out to be 3. And since 3 is odd, so we just make our answer as answer XORed with this element which is 4. And so what we do initially, we set a variable answer, and that initially has the value 0. So now our answer becomes 0 XOR 4, which is 4. Now we go to 7. Okay, we find how many subarrays are there which will be containing this element 7. So that will be 2 into uh, 2 into 3 minus 2 plus 1, which comes to be 2. That means 4, which is even, so we don't do anything. Now we go to 8. Okay, we go to 8. Now how many subarrays are there which contains 8? So that will be, so we are at the third index, so 3 minus 3 plus 1, which comes out to be 3, comes out to be 3. Okay, since this is odd, we simply XOR it with our answer. So answer is equal to answer XORed with 8. Answer initially was 4, 4 XORed with 8. Okay, that gives you 12. Okay, so that was also the value which we calculated initially here, 12. Okay, so this was the thing. Okay, I was talking of one more optimization, just a bit little more optimization we can do, and that is that, like, if n is even, okay, what happens if you just okay, let's try to analyze what happens if n is even. Okay, so if n is even, okay, then if you calculate the number of subarrays for a particular element, let's say a of I, then that will be I into n minus I plus 1. Okay, now if you consider even here, if I is even, if I is even, okay, so if I is even, uh, then obviously if I is even, then this thing, like I is even, so even multiplied by anything is also even. So obviously if I is even, then the number of subarrays will be even, and so in that case the element does not contribute anything. Okay. Now what happens if I is odd? Okay, I is odd. So if I is odd, then okay, uh, so if I is odd, so if I is odd, then what happens? Uh, then you calculate I into n minus I plus 1. But but you see, since n was even, okay, then even minus I was odd, so even minus odd is also odd, and odd plus 1, 1 is odd, so odd plus odd is even again this thing is even. Okay, so whether you calculate it for even I or odd I, the number of subarrays always comes out to be even, and that's why no element in the subarray contributes to the final XOR, and that's why the answer for even n will be 0. So whenever n is even, or you can say the number of elements is even, the final answer will always be 0. Okay, otherwise if n is odd, n is okay, if n is odd, then you see if I is even, if I is even, okay, so if I is even, then the number of subarrays will be I into n minus I plus 1, and since I is even, then obviously uh, the number of subarrays will again be even, and so since since I is even only, so again the even based indexes will not contribute. But if I is odd, then in that case we'll be having I into n minus I plus 1, and we know that n was odd, so odd minus odd, I is also odd, so odd minus odd is even, even plus 1 is again an odd, so this thing comes out to be odd, and so we would take the XOR. Okay, so as a summary we can see that whenever n is odd, our answer will be the XOR of odd based indexes. Okay, our answer will be the XOR of all the elements which are present at odd indexes. Okay, so as a summary uh, as a summary you can say that if n is even, if n is even, answer is always always 0, and if n is odd, then answer is the XOR of all the elements present at odd indexes. Okay, and here we are considering one based indexing. This is also one important thing. If we consider one based indexing, if you consider zero based indexing, everything will be just flipped out. Okay, but yeah, we are considering it in one based index. So that was all about this problem. uh, I hope you understood this problem. So thanks for watching.